Alrighty, guys, can you hear me again?
Yes, yes, we can hear you.
So we're going to change gears a little bit. As I've said a few times, like this year, we're trying to switch some of the material out and do a bit of hull. It used to be that hull would have its own separate course that you guys could choose an elective, but since the number of students has dropped, we try to provide some of this background material in 621, and you'll also see Professor Pham cover parts of hull in 622. Okay, so we have already talked a bit about the first couple of chapters. I'm not going to have anything to say about chapter 3. I'm skipping over, and today I want to talk about chapter 4. We're not going to go through all the individual parts here. There's something about swap rates. We're going to be doing that. We're going to be doing that a bit later. Right now, what I'll be focusing on is the different types of rates, risk-free rates, and how do these rates feed into bond pricing. Okay, so I'll be spending the next hour doing that. So. Okay. So we're switching over. This here is going to be Hall's chapter 4. So we're looking at risk-free rates, risk-free interest rates, and what we're looking at here is U.S. Treasury rates. Let's go Treasury. U.S. Treasury rates. So there are many ways to do this. There are lots of these rates. So there are several ways to compound interest. So let me just look at a handful of them. So if you say 10% annual, so this annual and yearly, you mean the same thing. If you put $100 into such a machine, into such a security, then at the end of the day, what you'll be left with will be 100 times 1 plus R. This is the way that we set up the money market account just before the break. So this is 100 times 1.1. So this is 110. You could do 10% semi-annually. So the way that changes things up is you put $100 in, and out here you'll get 1 plus R divided by 2. So that's the semi, and then you square it. And if you do that, you're going to get 110.25. You can put in 10% quarterly. So you put $100 in, and out you're going to get 100 times 1 plus R. But now quarter is something with 4, so you need something like this, and it's going to give you a higher number. This is 110, 38. So it goes from 110, 110 and a quarter, 110 and 38. You can do 10% monthly, So you put $100 in. At the end of the year, you're going to have 1 plus R divided by 12 to the power 12, and it's going to grow up to 110.47, right? And then finally, you can do the 10% continuously. But so you put 100 in, and at the end, you're going to get 100 times e to the R. So this is 110.52. So when you see the word annually, semi-annually, quarterly, and monthly, there is some effect on it. This continuously compounding, this is something that academics do a lot and is done less in practice. So let me talk a little bit about continuously compounding. Continuously compounding. But we have our money market account. All right, so that was the bank. We have our ST0, which is defined to be e to the RT. And often we write, and here's a new word for you guys, dynamics. And what that means is, if you take a derivative up here, you write dst is equal to st naught r dt. And then we take the starting point. We already talked about that the starting point would be 1. So what you're seeing here, this is like an ODE. This is a linear ODE. I will tell you what f prime t is equal to r times f of t. And that the initial point at times 0 is equal to 1. Right, so we have dst dt is equal to st naught times r, and then the initial point, that's when t is equal to 0 is equal to 1. And this gives you this linear ODE. And I'm hoping that you have seen that this here is the same thing as saying that f of t is equal to e to the RT, which is exactly what the bank account looks like. So this here is for a constant interest rate. So R here is a constant. Please note that I'm not saying that R is a positive constant. I'm not saying I'm just saying it's a constant. You can generalize this this expression here, and you will greatly do so later on, both in this course but also in other courses. You can have time varying interest. So if you have that, this S up here is not going to be just e to the RT. This here is going to be ST0 is going to be an exponential, but now there'll be an integral up here of RU du. And now R is a function. R is a function. It goes from time into R. And just as before, we can write this here in terms of an ODE. That we're going to be looking at now is here you have a t dependence, and the initial point is still going to be 1. So this is a function. You can also have stochastic interest rates. Stochastic interest rates is something we're going to be hoping, but so again, to just use Reeves textbook, right? stochastic interest rates, this is the last chapter that he has all the way over here in the end. He has interest rate, and so he has a binomial model for interest rates. Right? So now there will be stochastic interest rates, and this has a lot to do with fixed income. So in such a model, what you would have is you would have your ST, the bank account. It will still have the same form. It will still be this integral, but now the U comes outside. It's not a function anymore. It's a stochastic process where R U is a stochastic process. So this is a random variable. RU is a random variable. Each U. And of course, you can write this exactly as before. This here is the same, saying that D ST naught is equal to ST naught RT. So again, the T comes outside the parentheses and gets down here. And the initial point remains the same. It's always starting out at 1. So this is just terminology. You can have a constant interest rate. This is what we'll have in Black-Scholes. You can have time varying interest rates, and then you can have stochastic interest rates. As you can see from the example we had over here, it does appear like you start out at 110 and then the numbers increase and you end up at 110.25. So let me just show you how, I'm sure a lot of you have seen this this sort of agreement, this sort of limit. If I take an A inside the reals and I look at the limit as n goes to infinity of 1 plus a divided by n to the power n, that this limit here, this is exactly e to the a. And the way to see that is it's not too hard. You can switch it over, so you can substitute x for 1 over n and take logs, because log and exponential is each other's inverses. So now we'll be interested in the limit as n goes off to infinity, and then I'll take log. Log is continuous, so you go inside. So I'll have log in here of 1 plus a n to the power n. Right, and I want to prove that this is equal to a. I'll take log here, I'm going to get an a. And I'll switch it over, so instead of sending n to infinity, I'll send x to 0. So this is the same thing as sending x down to 0. And then log, there's a power here that's going to come down. I'll have x down here, and then I'll have log of 1 plus x here times a. And now I'm sending x to 0, so I have a 0 here. This is one of these 0 situations, right? I'll have log of 1 is 0, so this allows me to use L'Hopital. So now I need to compute derivatives. So derivative of x is 1. The derivative of log, this is 1 over 1 plus xa, and then I have to multiply by it. This is a chain rule, right? So I take the derivative with respect to x. It's going to give me log is 1 over, so that's this thing times the derivative of what's inside. That's going to give me an a. So this is an a, and then I have to take the limit as x goes to 0. And now you see I'm going to get my a. But this term vanishes, and I'm just going to get a over 1. This is an a, and this is exactly what I want to prove. So this is why we're seeing these numbers stack up the way we are. As I raise this power here, if I put a general n here, I'll have 1 plus r divided by n to the power n, and that thing has a limit, and the limiting object that you're going to get is this exponential of r. So we have these risk-free rates, and how do you get them? So you get these risk-free rates you get them from risk-free bonds. So that's in our world, US Treasury. I mentioned to you last time, I just saw an article about the debt ceiling negotiations that are currently going on, right? So the US debt ceiling, it has to be increased every time we get up to it, and it's only Congress that can increase it. And so now there's another push. The Republicans are not too eager to raise the debt ceiling, and so it's always this: is it really the case that risk-free bonds are US Treasuries? I mean, yes, so far in the past, this has been the case. But every now and then, the debt ceiling in the US has to be increased. And if the debt ceiling doesn't increase, then ultimately the US cannot issue new debt. And that means that we can't pay, we can't maintain our current debt. And so then it brings into question whether or not risk-free rates are really the ones we get from US Treasury bonds. So if you're following the news, try to pay attention to the negotiations related to the debt ceiling. This has to do with this statement here that you get risk-free rates from US Treasury bonds. Okay, so how does one go about doing that? Let's look at a little example. If you have a risk-free bond, so say a 5-year risk-free bond, trades as follows. So you have the picture, like you have the payoffs are coming out here at the end. So this is 5 years out. And the payoff that's going to come is $128.40. Like this here, this is coupons and notional. The risk-free bond is trading at 100. So what is the implied risk-free rate? So this here is at time 0. And so the implied risk-free rate over that period, 5 years. Well, what is it? Well, you'd have to take $100 times e to the r times 5 if it's continuously compounding. Continuously compounded, and then you want to end up with 128.4. So what you do is you divide over and you take log on both sides. This is the same thing as saying that R is 5%. Now you could have done something else if you were to say the implied risk-free annual implied risk-free annual rate. Well, this is a different story. you're still having $100. You put $100 into this bond. If you have an annual rate, then you will have R wouldn't be given like this. It will be given like 1 plus R to the power 5. You get R every year. You can put it in for 5 years. You want to get this out as 128.4. But now this is much harder because this is a 5th degree polynomial. This is a 5th degree polynomial, right? And the other one was much easier. So you're starting to get a sense of why we're working with continuously compounding, because solving this thing here, this is not particularly pleasant. So let me just show you how one can go about doing it. It's a 5th degree polynomial, right? So there are 5 roots, there are 5 possible values for R. I'll try to show you how to do this in Mathematica. So we are down here somewhere. I wanted to solve 100 times 1 plus R to the power 5. I want this to be equal to 128.40. And the free variable is my R. So I want to solve this. And you can see it's a 5th degree polynomial, so it'll give me 5 roots. Of course, we're only interested in this guy over here. So I see here that I have an annually compounded interest of 5.13. So it's doing this on a piece of paper, this is difficult, but doing it on a computer, this is not difficult. I also had an annual rate, and of course I can write this here as R being 0.0513. So when you have quoted prices, US Treasury, when you have quoted prices, bond prices for US Treasuries, you can back out here what this implied interest rate is. We're going to look at another example in a second where this is more complicated. This here was pretty simple because you were only interested in backing out this one rate that will work over a 5-year period. And the more complicated example is going to have, I think, 4 or 5 of them. So there's a little bit more work to be done. The other thing I wanted to say is you often see the words, see phrases like yields. So for example, when the bond is not risk-free. So when you take out a loan, I take out a loan. So this could be a mortgage. It could be California debt. It could be Greek debt. It could be Microsoft debt. It could be any kind of these things. So California has a sizable economy and they have debt. So they need to take out debt. Is California able to default? Yes, it is. This is not considered risk-free. When I take out a mortgage, I can default. Greek has been in trouble in the past. They have debt. And Microsoft, of course, is a private entity that could also default. So when the ball is not risk-free, sometimes one considers, we consider yields. This is denoted by Y, and this is typically positive, right? So let's do an example. You have a bond traded, so issued either by me, so it's a loan, mortgage, California, or one of these other entities, and it has the profile. It has the profile. So here at the end, The end in this example is 2 years. And the end payment is 103. And so 103, as before, this will consist of coupons and notional. Notional, another word is principal. Maybe it's 3% coupon and notional is 100. And then at earlier times, at time, say 1.5, and at time 1, and at time 1/2, I'll just have coupons. So the payments that will be coming in here would be if $3 is the coupon. Right, so the profile, this here's the promised payment profile that say I have on my mortgage. I'll promise to pay 333 and 103. And now how much is that worth? What am I able to get out of that at time 0? Well, say that what I'm able to get out of it at time 0 is 98.39. Right, this is the current price. So what would the yield be? Like, this is how much I can get today by promising to make a payment of 333 and 103. Somebody's willing to give me $98.39 in return for my promise to pay 333 and 103 at these 4 future time points. Well, the yield, let's do a continuous yield. So the continuous yield, it'll be 98.39. It's the thing that I'm going to be discounting these payoffs with. So I'll take e to the minus, but I'm moving it from here over here. So I'll take e to the minus, and then I'll treat this as a constant. So this is the same coefficient that I'm going to be using for all these 3. This first one here comes at 1/2. So this is times 0.5 times 3. The next one is the same coefficient, but now coming at time 1 times the $3. And then at time 1/2 times the $3. And then finally, I get something at time 2. Get something at time 2, e to the minus y times 2. Like, this here is the equation that the yield corresponding to this profile must satisfy. And so this is one equation and one unknown. You solve, you're going to get a yield of 6.76%. So that's what a yield is. It's typically something, the yield is typically higher than the risk-free rate because there's a risk involved. Had this been risk-free, so had it been issued by US Treasury, this number here would have been much higher. Oh, sorry. Yeah, I missed that coefficient here. 103 over here. Thank you. Yeah, so again, if I would have, if it's issued by me, and this year is, I promise to make 333 and 103 dollar payments at these future time points, I can land 98. But if US Treasury says I'm going to be paying 333 and 103, the number that you can get out here is typically much higher. Indeed, if 3 is the risk-free rate, then you should have 100 out here, right? And then the yield should drop to 3. But I have risk in me. I get less money because I might not be able to make these payments. Any questions on this part? So let's go back to this more elaborate example that I alluded to earlier, where I said that let's do something that is more involved here. Paul calls this bootstrapping, so I'll continue to call it bootstrapping. Let me just show you what it is that we're going to be doing. So it's over here in It's chapter 4. It's this table we have down here that I'm going to try to recreate. So what we're trying to do now is create this curve here. These are these rates that we're looking at. So we're going to have a time horizon from, say, 0 to 3 years. I'm going to try to figure out what the interest rate is by looking at data. So this here's the data. I have how many bonds? There are 5 bonds available. And he calls this method that I'm going to go through now for bootstrapping. So we imagine that we have these bonds here. They're traded, right? So these are the prices that we get to observe. There are bonds of different maturities, a quarter, half, 1, 1.5, and 2 years. And they have, some of them have coupons, some of them do not have coupons. Right? And they're traded for a specific price. Now, based upon these 5 bonds, can we create this risk-free interest rate curve? That's called bootstrapping. Let me try to show you how to do that. So bootstrapping. And this is a Hall's table. This is Hall's table 4.3. So there are maturities that we're going to be looking at. This is my timeline. So I have 0, I have a quarter, I have a half, I had 1, I had 1.5, and I had 2. I'm going to try to create the interest of these 1, 2, 3, 4, 5 time points. We start out at time a quarter. So in dynamical programming, you would go in this direction. So for bootstrapping, you go in that direction. The first instrument we have available trades at 99.6 There are no coupons attached to it. It pays out 100 at the end. Okay, so then I discount it back with the risk-free rate. These bonds are issued by US Treasury. So I discount it back by the interest that is working here up to time a quarter. So that's R of 1/4 times 1/4. So this is one equation and one unknown, and I solve, and I'll get that R at 1/4. This is equal to 1.603%. So the first 3 bonds do not pay any coupons. You only have this payment at the end of 100. So the next one is at a half. That one is trading for 99. And I solve a similar equation. I'm just getting it, the payment, instead of getting it at a quarter, I'm getting it at half a year. This is minus R over 1/2 times 1/2. I'm doing continuous compounding. So R of half, solve this equation, divide over, take log, and I'm getting 2.01. So that's my second interest rate. And the third one is also of this similar type. I'm now at a one year horizon, and we're going to get 97.8. This is $100, and then discounted now out to 1, and I can solve for that interest rate. It was 2.225. Is that right? 2.225%. So the next bond is more complicated. This is where the bootstrapping comes into play. How do I put these things together when I have a more complicated scenario? Here I'll have payments. So this is, now we are here. And the payment profile is at a half, we're going to get $2. At 1, we're going to get $2. And at 1.5, we're going to get 102. And the price that this instrument here is worth is 102.5. So how would we go about doing this? Well, we use the same formula as before. This is a risk-free bond. So we move these payments to time 0. Okay, so I'll write 102.5. And then I need to discount the 2. And I'm using continuous compounding. So this is e to the minus. And then the interest rate that works at time 2 is r½ times a half. Plus the next payment, this is coming, this is $2. It's coming in at time 1. So I'll do the interest rate up to time 1. And then the last payment, e to the minus r of 1.5 times 1.5. This is my equation. And the bootstrapping, the word bootstrapping has to do with the fact that I already figured out what this one was. This one was 2. Did I mess up my numbers here? This one here was r½ was 2.01%. This one here was 2.25. And this one here is the unknown. We have one equation and you solve. So you solve for r 1.5 and you're going to get 2.284%. So that's the bootstrapping element. Like you take these previous ones that you have computed and you plug them into this one. He does one more, so let me do that one too. Go all the way out to 2. So there's a new bond out there, again issued by US Treasury. The payments are 105. This is the initial value, and then there are payments at time a half, 1.5. I think all 2.5. And then the last payment is at 2, and this is the big one. So this bond is trading. It has these 4 payments, and the value of these 4 payments is equal to 105. And so what we do is exactly as before. We would have 105 on the left-hand side. We'll put in 2.5 times E2, and when do we get the payment? Is at a half. So we have that part. Same thing for the other ones. Two and a half, e to the minus r, 1.5 times 1.5. And these are quantities that we already derived. And the last one is 102.5 times e to the minus r of 2 times 2. The first ones, we already know what are. This one here, this was 2.01%. This one here was 2.225. And this one here was what we just computed. This was 2.284%. Right, and this one here is now the unknown. And we solve, we're going to get that R2 is 2.416. So now we can fill in the points in a diagram. So we have time here. We've been able to get 5 time points. So we have a quarter, we have a half, we have 1, 1.5, and we have 2. And they move as 1.6. That was that guy. Then it moves up to 2. Then it moves to 2.2. Then it goes up to 2.28, so a little bit higher. And then 2.4. So it looks something like that. These are the 5 points that I implied for the 5 traded bonds. And how do you get a value, say, here? What happens if I want to have a value here at 1.25, 1.25? Well, one way to do it, and this is what Hall suggests, is that you go up in a straight line. So you're right in between these two, 1 over 1 plus 1 over 4. And so what you do is you connect these here with a straight line, and that's going to be your value there. So you can, so between points, you do a linear interpolation. And then nobody says that it should be linear, but this is what he suggests. And then to this here's Hall's suggestions. Between points, you do a linear interpolation, and then outside. So if you were out here with 3, what would you do out here? So outside, you're just flat. So what he suggests is that if you want to be out here at 3, what you're going to do here is, this is just a flat line. And likewise, if you were in here, this would just be a flat line. And in between lines, you go off these linear interpolation curves. This is Hall's suggestion to create the interest rate curve. Any questions on this part? So many years ago, there was a group of researchers that asked the question, like, is this a good idea? So so in the 90s, Björk and Christensen asked if this is consistent with NOAB. So in the 90s, like this book here by Hall, this 10th edition, I think this came out in 2010, if I'm not mistaken. This came out in, no, it came out much later. It came out all the way up in, all the way out in the 2018. Okay, so 2018. So this book here is much newer than this research here from the 90s. So Thomas Björk and Ben Christensen, they asked this question: can you just do this stuff? And what about no arbitrage, right? We have talked about no arbitrage. You should probably make sure that this is consistent with no arbitrage. And and this here is problematic. This is what these scratched here in this paper shows that one has to be really careful about doing this sort of interpolation, this sort of bootstrapping. That being said, this is really what people do in practice. But from a theoretical point of view, Thomas Björk and Ben Christensen, they pointed out you have to be a lot more careful about doing this if you want to be consistent with no arbitrage. So this will take us far outside the scope, but if you're interested, just look up you only wrote this one paper together. So it's an easy reference to find. Alrighty, are there any questions or comments on these interest rates? How one gets them from data? All right, we have a little bit of time left, and let me just. There are other interest rates. Let me talk a little bit about it. So one thing that Hall mentions is these forward rates. So a forward rate, we're sitting here at time 0, and then there's a time 1, and there's a time 2. Right, so what you want to do is you want to log in. You want to log in, not log like that. You want to fix a rate at time 0 for a loan between 1 and 2. And we just give you an example on how to calculate this. If you have, say you're given 2 bonds, a risk-free issued by US Treasury. You have the profile. So you have the profile at a time 1, you're getting 103. Right, and this moves you back to 100. So that's one bond. The other bond, there's a payment at time 2. That payment is 108.33. That's the one we had before, and it'll give you $100 over here at time 0. So the way to get the forward rate that works from time 1 to time 2, when you know rates that are working from time 0 to time 1 and from time 0 to time 2, it is simply just to compare. Right, so what we can do is first figure out what these two rates are. Like, so 100, this is equal to e to the minus 0.03 times 103.05. Right? So that interest rate that works here is 3%. So R1 is 3%. Likewise over here, this is the one we already had. The interest rate that works from 0 to 2, this was e to the minus 0.4 times 108.33. So R2 is equal to 4%. So the way to get your hands on that forward rate that works from here to here, it is simply just by saying you can either put $100 into the 2-year deal. You can either put $100 into the 2-year deal. It's 100 times that continuously compounded interest rate of 4. This is going to give you that 108.33. So you can either do that, or you can do 100 into the 1-year deal. For a year, and then you stick it into that. And then you stick that amount into the forward rate agreement that works from 1 to 2, and then it'll be in there for a year. So you work out what this is. This was 103.05 times this continuously compounded forward rate. So these two things, they have to be equal. So you solve 108.33 equals to 103.05 times e to the RF, for RF being 5. This is the average. This is the average of, like, I have 3 here for 1 year, and I have 4 here for 2 years. So I'll need RF in this continuously compounding setting. I'll need RF to be 5%. So those are forward rates. Those are rates that you lock in at time 0 for a loan that's going to start at time, in this case, a loan that's going to start at time 1 and it's going to end at time 2. The final thing that is in this chapter that people care about is, so again, forward rates. This is, we will see forward rates when we get going. This is coming over here, and it's going to come over here in towards the end. You can see there's something with forward measures, futures. So this is going to come over in the stochastic interest rate section towards the end of the course. Another thing that he mentions, the last thing that he mentions in this chapter that people care about is duration and convexity. So this is again related to a coupon paying bond. So you're looking at a yield. So for a yield, we're looking at not necessarily risk-free bonds, but for a yield, we will have that the bond price is equal to, so the picture is, here's where we have B. This is at time 0, and then at time 1, T1, you'll have a coupon payment, C1, at time T2, you'll have another one, C2, and so on, all the way down to the end. You have a TN, and there'll be some CN payment. Right, so the yield is the thing that will move all these back to time 0, such that the prices line up. You have the sum from 1 to n, and then you'll have the coupons and notional, CI, and then discounted by the yield times TI. That's the formula. This is what the yield satisfies. This is that constant, such that when you plug it into this formula, you're going to get exactly the value of the bond at time 0. So these dollar payments, when you move them back, they will line up exactly with the initial bond price. So the duration, to get that one, what you do is you just take a derivative with respect to y. So when I'm taking a derivative with respect to y of b, I just take a derivative here on the right-hand side. So I'll get CI, doesn't depend upon, there's a y here, so I'll get a minus a TI down, and then e to the minus y TI. The duration d, this is defined as this expression you have up here divided by b. So b, and drop the minus sign. So CI, TI, e to the minus y, TI. It is this coefficient. And the reason that you're interested in duration is you have a derivative up here. So if I'm looking at small changes, so for small changes in the yield, then the change in the bond price, this is the change in the bond price, this can be expressed in terms of, well, you have your B, and there's going to be a minus sign, right? Because there's a minus sign up there. The minus sign is not here. So this will be minus B D delta Y. So for small changes in the yield, the change in the bond price is proportional to the change in the yield. And this is coming from this derivative. And so to make this more accurate, you can look at convexity. And convexity, well, then you just compute, instead of first derivative, you compute a second derivative. You compute a second derivative. And if I compute a second derivative here, the only thing that changes is that I'll get another minus sign down, and then I'll have another TI coming down. So this one here will be, I'll have my CI, and then I'll get another derivative, so it'll be TI squared, e to the minus y TI. So the convexity C, this is defined as roughly the same formula as this one here, but now just with squares. So that will be C, this is 1 over B, and then just the squares. CI, but now with a square up there. And so we can improve the formula. We can improve the formula by saying that, including a higher order term, we can say that delta B is approximately equal to minus B d delta y. That was what we had before. And now we divide it by 1 here. So if you want to go 1 up with Taylor, you need a B squared. So we only have 1, so there'll be a B there. And then there'll be a C, and that's probably a half from Taylor, and then delta y squared. Right, so this one here is the first order Taylor. And this one here, when you take the second order effect into account, this one here is a second order. So you can, these measures, duration and convexity, one application of them, if you know what they are, the D and C, is that you can use them to approximate changes in the bond price. So you can look at sensitivity of the bond price with respect to yields. And as soon as you want to have sensitivity, that means computing a derivative. Okay, I think this is all I had. This is all I had for today. Are there any questions, comments about what we've been doing? If that's not the case, then we will have we'll have office hours later this week. The TA has office hours Wednesday and Thursday, and I have office hours on Friday morning, and everybody's welcome to bring their questions, concerns about homework, lectures, material, and so on. Otherwise, I will see you guys next Tuesday.
Thank you, Professor.
You're welcome.
Thank you.
Welcome, guys. Have a good night.